Hi, everybody. My name is Kyle, and today we're going to be talking about the essentials of search. And we'll be talking about it in reference to OpenSearch, but a lot of these are conceptual ideas that we'll be able to use in any circumstance in which you're thinking about any search engine. So we hope there's transferable skills, but we also hope you look at OpenSearch. So before we get too deep into it, let's go ahead and take a look at our agenda. So the first thing we're going to do, we're going to talk a little bit about the project. OpenSearch is a newer project, so it's important to kind of put out there exactly what we're going to be talking about and what project is the kind of target of this. And then we'll go into the search concepts after that. And then we'll dive into how you can get involved and contribute to OpenSearch and how you will get involved going forward with it and how we'll be able to communicate on it. So before we go too far into each one of those pieces, though, I do want to spend some time just introducing myself. My name is Kyle. This is what I look like on a normal day. I've been telling people it's true. I got word this week that my barber has gone out of business due to COVID, and I think I contributed to that because I've been giving myself home haircuts this entire time, and I don't look quite like I did when that picture was taken. But when we meet in person, I'm going to look more like this. Um, I'm Senior Developer Advocate for OpenSearch at AWS. I was actually hired for a slightly different role for working with a different project, which we'll get into in a few seconds. But now I work exclusively with OpenSearch. And just to give you a few things about me, I usually do this in numbers. It's just a little bit nicer than talking about myself in bullet points on a slide. So 92 represents 1992. That was when I first started getting serious about writing software. At that age, I probably should have been riding a bike more, but I was really interested in compilers. And once I started using a compiler, I thought this is the most interesting thing in the world. And that really, that's how I got bitten by the bug of writing software. I actually wrote a compiler when I was very young in 92 and released it as shareware. I usually tell people this because I hope somebody is digging through something and ends up finding that piece of software. I have lost it. It's something that I really want to look at and cringe completely at. 241 is the number of days I've worked at Amazon. So I've been in this project or in this role for a relatively short amount of time compared to many people on the project which have been here a number of years. Three are the number of search engines that I've worked with in the past. Previously, I worked with a couple of Redis-based search engines, and now I'm working with OpenSearch. So I find the search domain really, really interesting, and I think it's one of those things that, again, I got bitten by the bug, and now I kind of think about it all the time. 53 is the a parallel that I live at. I live in Edmonton, Alberta, Canada, which is a great place. It's the northernmost city in Canada, and as you can imagine, it's pretty cold up here. But in summer, right now, it's beautiful. So if you ever want to visit, don't come in the winter. And 8 is the weight of my dog. So I tell people that because we are presenting right now, and my dog knows not when I'm recording. So if you hear a dog barking in the background, that is my 8-pound dog, Mr. Button. He's a 12-year-old Italian Greyhound. And if you end up following me on social media, which I suggest that you do, I talk about 3 main topics, and that's my dog, 3D printing, and search engines. So I hope you like all 3 if you do follow me. Now I'm going to hand it over to my co-presenter today, and that's John. So John, take it away.
Hello, everybody. Thanks for coming out today. My name is John Handler. I'm a Senior Principal Solutions Architect at AWS. I don't have quite as elegant an introduction in numbers, so I'm going to wing it a little bit here, and I'll just say that I've been working at AWS for going on 11 years now, and mostly focused in the search space, all focused in the search space. I've been a solutions architect and for our Amazon Cloud Search product and our Amazon Elasticsearch Service product across the last 10 years. Also, I have search as a primary passion. I think the problem of I have an enormous pile of information and somebody's going to come and through a very small window give me a question, and now I have to go figure out what's the answer is a deeply, deeply fascinating question. And so it really motivates me and really makes search a wonderful technology for me. I am working with the OpenSearch and Amazon OpenSearch service products going forward. So happy to be here today and to talk about sort of the essential concepts in search.
Thanks, John. Now, John's going to be with us to talk more about some of those concepts here in a minute, but I'm going to talk a little bit about the project. John and I have a lot in common beyond this project, but one of that is that we're both really interested in search engines, it's really fascinating when we look at this particular product because we're going to be talking about something new, and I think that's really the thing that surprises people about this is how this project happened and the parameters around it. So OpenSearch is, and I'm going to read this verbatim for just a second. Normally not something I do, but OpenSearch is a community-driven open source search and analytics suite derived from the Apache 2 licensed Elasticsearch and Kibana in version 7.10.2 of each. Now, it consists of a search engine daemon, OpenSearch, and a visualization and user interface, OpenSearch dashboards, as well as a series of functionality adding tools and plugins. So what does that all mean? Let's talk a little bit about the contents here. So derived from the Apache 2 license, Elasticsearch 7.10.2 and Kibana 7.10.2. Basically, what happened is earlier this year, Elasticsearch and Kibana had a license change. Those license change means that they moved to a license that was not open source anymore, and that's very important to a project that I worked with, which was Open Distro for Elasticsearch. And Open Distro for Elasticsearch actually took Elasticsearch and Kibana, the open source versions of those, added in a number of functionality through plugins, and created a kind of a different set of features for that. They were all open source. So obviously, when there was a change away from that in the upstream for Elasticsearch and Kibana, we wanted to continue forward with the same type of tool, and we forked Elasticsearch and Kibana from their last Apache 2 licensed versions. So the team went through and removed instances of where there was mixed licensing. So Elasticsearch and Kibana had mixed licensing in the repos, and so we had to extract anything that wasn't Apache 2 out of it. And then we renamed it, of course, and removed anything else that was associated with the previous project. So things like build tooling, metrics and telemetry collection that were built in, and just all the stuff that really wedded it to the previous Elasticsearch and Kibana. And now we have OpenSearch and OpenSearch dashboards to move forward with. So let's go about, maybe I've told you a lot about this, but how are they used, right? And this particular talk has a few specific things that we'll be going over in this, few use cases for it. Log metrics and trace analytics. So this is the analytical suite part of this. Generally, these are machine-generated data that comes from one process to another. It is then indexed in OpenSearch, and then the OpenSearch and OpenSearch dashboards are used to find things in it. Now, the other use case is enterprise and general search. Now, this is kind of where, if you look back in history of where this project came from, and from the inception of the preceding project, this is where it kind of started, was for general and enterprise search. This is more what you'd think of as finding information in documents, finding information in, say, a product catalog. So these two things look a little different, but in fact, many of the internals to software would be very, very much the same. So that's why they are together under this. And now, if we were to think about this from a perspective of, who do we expect to use this for? We expect more people to, in fact, use it for log metric and trace analytics, and indeed, probably a much higher volume of people doing that because machine-generated data is much larger. But we still see an important core group of users who will use this for enterprise and general search. So moving forward to the license, I've touched on this a little bit, but the entire project is licensed under the Apache License version 2, ALV2 as we like to call it. And it gives you these kind of well understood ways to use it. So you can use, modify, extend, embed, resell, and make it part of your own product or service. So that's really important to us, and we're kind of playing by our own rules here. in that at AWS, when we have our service, we will be using, we're well under this license as well. But we encourage other people to do this as well. So that's the thing about this, the software, we're not selling licenses or anything like that. This is just a open source project, and we hope everybody can use it. Now, the one thing about this is there is one exception to the everything Apache version 2. The website, which is open source, is BSD 3-clause license. It's got a different history, so it is a little different. Now, where are we in this? As far as the status of this, we have a number of different steps we've gone through. In January, we made the announcement that we were going to fork. In April, we introduced the fork to the world and the name to the world and gave it an alpha version. So that's where you can look at the source code and build it yourself. Now we're moving into May. We should have a beta release out either as you're speaking of it now, maybe around the same time. That date has floated a little bit in the course of recording all of our talks. So I'm just saying May right now. But then we'll move through beta 2 release candidate stage, and then finally in summer 2021 will be at general availability. Now, as it was pointed out to me, summer 2021 is Northern Hemisphere centric, so you could also call this mid 2021 as well, because summer would be winter in the Southern Hemisphere. Now, just a little bit more about the project. OpenSearch is a distributed search engine daemon. We use that kind of terminology here for a couple of things. It's distributed in the fact that it can exist on more than one physical machine or virtualized machine. So it is not limited to only performing its duties on one machine. It can be sharded out into multiple different pieces, which we'll get to in a little bit as well. You interact with OpenSearch via REST API. This is something that is a little confusing for folks. Often say, like I was in OpenSearch and I clicked on this. And every time I hear that, I'm like going, okay, no, that's not exactly right. That's something different. You interact with OpenSearch through the REST API, which you would just use HTTP request or HTTPS more specifically, and then your path, and then the payload that's included in that request tells the server what to do and how to respond. It does performing of indexing and storage of data. What I mean by that is, while that makes it sound like a database, and later on we're going to say it's a database, its primary role is different than what you may think of as a database. Its primary role is to index data. Storage of data is also there, but when you see indexing and storage, people think of it as the same thing as your run-of-the-mill database. But when it comes down to things like consistency model and transaction guarantees, it's quite a bit different than maybe the SQL database you're using for your primary database. It is built in Java using Lucene. Lucene is a well-established and at this point I think a couple decades old library that has constantly evolved over many years to provide like the core functionality of search. So we owe a lot to the Lucene project, and that really powers a lot of the things that we're going to be talking about today. Now, OpenSearch Dashboards, on the other hand, is the browser-based UI and visualization platform for OpenSearch, and it only really works with OpenSearch. So it has built-in charts and table representation that you can kind of compose into dashboards. And that's where the name comes from. That's what its primary use is for. It does have a lot of other uses as well, like you can kind of manage to some degree OpenSearch from it and all the features that are in there, but you can also use it to put together that at-a-glance view of data. And that really comes into when you're talking about logs, metric, and trace analytics. That's what it's used for. For what we're talking about in this presentation, it's not as relevant, but it's still useful. You can interact with OpenSearch directly, basically kind of applying the REST API into a portion of OpenSearch dashboards and kind of interact with it as if you were interacting with it through curl with just a few extra things. Makes it a little nicer to use. If you've ever tried to format a lot of JSON in curl, it's not fun. Or you can use DQL, which is the dashboard's query language, which simplifies a lot of the things that you might have in the DSL, which is the way you would normally interact with it. It's built in TypeScript And so it runs on the Node.js runtime as opposed to OpenSearch, which runs on the JVM. So they are kind of developed somewhat independently, but they are developed to work together. Because we have two different kind of languages, they don't share code, and they have different teams working on them. So it's an interesting way to see this, and you'll see later on how this has an effect on some of the other things that are in the project and how we develop those. Now I'm going to hand this over to John. He's going to talk about the concepts of search, and we'll just go from there. All right, here you go, John.
Thanks very much, Kyle. So, as I mentioned in the introduction, the kind of search itself is a fascinating problem to me. And, as we look at sort of the growth of the web and the growth of sort of the technology and mobile technology, and the search bar itself is really becoming a core necessity for any application, and has to provide good relevant results for user queries. And so I'm going to talk a little bit today just about how the data goes in, how it's structured, how it's retrieved, and how to make good results come out of that data. Let's go ahead to the next slide. So, and backing up a second, really this search workload is kind of the core for OpenSearch. As I said, the search box itself has become ubiquitous. We all expect a search box out there. And, funny enough, if I'm walking through the supermarket and I can't find the whatever, I'm looking around in the air for that search box that I can just type at and find the thing that I'm looking for, right? It's become almost a necessity to us. And when we translate that into the technology and application world, really what we have is a primary store, and we'll get to this, which is a catalog. Let's say that grocery example, or let's say a movie example, which we'll come to also. I want to go find a movie on some streaming service that I'm using, right? I'm going to search for it. Well, on the back end, I'm going to have a primary store, which has all of my movies in it. That's a relational store. And then I'm going to have a search engine, which will provide that rich and relevant search against the data that's in that primary store. When we use OpenSearch for search, you're going to load your data in, and you're going to use those REST APIs to query that data and bring the relevant results. OpenSearch as a technology supports, sort of a full suite of search features. Rich query language that enables you to really accurately bring a query in, adjustable rankings so that you can build a good relevance, and as well as special processing features and a differentiator from other databases, the ability to really treat natural language and bring it out into terms so that they're targets for matches. Next point. Now, because of the ubiquity of search, we also had a lot of folks who thought, well, it'd be a great idea to send my log data into a search engine, right? I've got a jillion servers out there. I'm generating all kinds of logs. I have some kind of error. Well, you know what? I want a search engine to go find that error. I don't want to have to log in sequentially and grep my log files to try to find the actual problem. And so, you're with a log analytics workload, you're bringing in that log data, your metric data, your trace data. That's going to enable you to build the dashboards on top of it, as well as run queries against it. OpenSearch really, and developing out of sort of Elasticsearch, has a much greater capacity to ingest data, which makes it suitable for these kind of log workloads. And with OpenSearch dashboards, you are able to bring visualizations in near real time as you're flowing that data in. That's all I'm going to say about that. We're going to put analytics workloads to the side for a second, and then just proceed sort of with the search use case. So OpenSearch is in the database technology world. This one, it is a database, but it is not a relational database. Kyle already mentioned the lack of transactions. It doesn't have a read after write guarantee. And also fundamentally, it's not a hierarchical or a relational kind of technology, right? It is a database, but it's not a relational database. It's more like a NoSQL store. it has a very familiar interaction model, right? So you're going to send your data to OpenSearch via JSON, via those REST APIs. Next point. Then OpenSearch itself is going to create indexes on all of that data. All of the fields in the JSON are searchable. This is another differentiator for OpenSearch versus other database technologies. The indexing is automatic and assumed. So even down to nested JSON, you're able to get dot path access to those fields to provide search against them as well. Next point. And then on the query side, you're again going to use that REST API to do fielded matching along with complex expressions. You can do sorting, you can do analysis of the data based on sort of aggregations and group by that give you a means of doing numeric and other analysis on that data itself. The index is the core structure within OpenSearch. So when you send your data in, actually the core structure really is the document. So the document is that JSON blob that you're going to send for indexing. It consists of an ID that's associated with it, along with a set of field value pairs. You use that REST API to send that document into an index. The index is the organizational piece. It's a logical, not actually physically realized. It's a logical structure that enables you to gather collections of documents, right? I think we'll talk to this later a little bit too. You can make the analogy that an index, you make that analogy, then a document is like a database row in a more relational database, right? And then of course your fields are the columns and your values are the cells, right? So fields and values in JSON, again, the fields and values are like the columns and cells. Next one. And so we've made this analogy that the index is like a database table. Having made it, I'm going to caution that just like OpenSearch is not a relational store, an index is not exactly a database table. And we'll get into some of the ways that it differs next slide. So starting with the document, we're going to imagine a case where we have one of these streaming services and we have these entities, which are movies. We really want our customers to be able to come find the movie that they want to watch and then be able to purchase and play that movie. So if we think about the movie entity has a number of different pieces of information associated with it, right? So movies have a title, they have a year they were released, they have a rating, they have genres that they're associated with, maybe a little plot description, actors, directors, etc. When we start with this entity, and when you use OpenSearch, what you're going to do is take all of those pieces of information and format them as JSON, where the field is going to be the particular piece of information. The value is going to be the actual value for this entity. And this search document then is the core of how you're going to interact with your data set. So if we translate the prior movie sort of view, the image view, into JSON, it's going to come out something like this, right? We have our ID, we have our title, our release date, actors, directors, etc. This is, again, the document that you're going to send to OpenSearch to support searching against these movies. Internally, then, OpenSearch is going to create an index for each field. So as I said, differentiator from other database technologies, indexing is automatic and universal, right? If we have our document with our fields and values, right? So the JSON has our name value pairs for the document itself. This is, again, title, actors, directors, etc., right? OpenSearch is going to, for each of those fields, create an index. Little bit confusing. We have index as a name at two different levels of hierarchy, but the field indexes are what are actually supported by Lucene. And the field index is then going to take, for each of these fields, every value that has been seen for that field and create an entry. Each of the entries then points at the set of documents that contained that value. So you can really think of something like an encyclopedia. We don't really have encyclopedias anymore, but back when encyclopedias were paper things and you had an index and maybe you wanted to look up like Barack Obama, the index would contain an entry for Barack Obama, and that it would point at the set of pages where Barack Obama occurs. Same thing for the index in OpenSearch. You have the values, which is like Barack Obama, and maybe it's other presidents, what have you. And then the posting list is the set of documents that contain those values. I've left out the bar in the middle, the analysis bar. We're going to talk about that in some depth. Fundamentally, you're going to assign a type to these fields, and that's going to tell OpenSearch how to decompose the contents of the value. You have a lot of different types in there. You have native numeric types, you have geotypes, you have text types, IP types. There's a lot of different types that it can be. The process of moving from the raw value to the indexable value is called analysis, right? So for each of these fields, you're going to analyze the value. That's going to give you one or many terms, which are the entries in the index, and those point at the posting list. All of this, I know I'm dwelling on this a little bit of time, but this is really the core data structure that drives the search engine. And this is how we support retrieval through looking up values in the index and then performing set math on the posting list. So this is the core data structure and really the way to understand search. And whether you're using it for logs or using it as a search engine, this will come into play, both for performance and for understanding what you're batching, for understanding your relevance, all of those things. So the data itself, the index, again, is the top level structure. And one of the differences between an index and a database table is that indexes are natively partitioned within OpenSearch. So when I create an index, I'm going to set a primary shard count. That is going to control the partitioning of my data into multiple pieces, which OpenSearch will then distribute across the hardware that I provide for the processing of the data. So the concept of shards and the way that you decompose your data into partitions has a critical downstream effect on the performance overall of your OpenSearch cluster. When I set, for instance, 5 primary shards, then my data is distributed randomly by default across that set of 5 shards. OpenSearch also supports a notion of replication, as do many other databases, but the replication happens within the index. So I've created an index in this slide of 5 primary shards. I can add 1 or more replicas, which will be full sets of those primary shards. Those replicas, for the first one, it provides a redundancy. OpenSearch won't put the primary and a replica onto the same node in the cluster. And then that ensures that should you lose a node, you retain a copy of the data in the cluster, and OpenSearch can recover and recreate copies and promote to primaries. So the concept of sharding is, again, important both for the understanding of the processing of your data and also the performance of your cluster. Again, in a very typical sort of database interaction fashion, you use query APIs for querying your data. OpenSearch has a query language, which is, again, JSON and REST-based. You're going to use a GET request with your endpoint, an index name, and the search API. In this case, we're doing a simple query for Iron Man in the title field. And OpenSearch is going to match that and retrieve this along with other documents that match Iron Man. Understanding how you are matching is really critical to understanding why you're getting the search results you're getting and how they're being scored and sorted. As I mentioned, OpenSearch has capabilities for handling natural language and for decomposing text and bringing out, language-specific features that enable better matching and better retrieval of information. The first thing is, during the analysis phase, OpenSearch is going to tokenize the data. There are a number of different tokenizers. Again, some of them language specific, some of them more general. In this case, we're using a white space tokenizer and taking the text that is the plot description, and OpenSearch will decompose that into a stream of tokens that are all of the white space separated elements of this particular block of text. Of course, capitalization is not particularly relevant in terms of matching. Whether I type capital I iron or lowercase I iron, I still want to match iron. And so when OpenSearch is processing this text, it's going to apply a filter to lowercase all of that text. So you can see here we've lowercased the W and when at the start of a sentence. This just opens up more matching and removes the irrelevancy of capitalization. Along with that, OpenSearch supports a concept of stop words. Stop words are low value terms and low value in the sense that many or most documents have them. So if I'm going to match a term like an, that will probably, or if I'm going to query for a term like an, that will probably match every document nearly or really that I have in my corpus, right? So its presence in a query is actually not helpful, and the match for an is not actually helpful in retrieving the correct results. A stop word during indexing is a removal of those terms from the text itself. So in this case, we're removing is and to and an and a so that we have a richer base for matching against. Then we apply what's called stemming. With a stemmer, we're reducing the terms to root form. Again, this is going to expand the range of matches that we have for that particular piece of text. And as an example, we have here wealthy, but presumably the concept is the same, whether I say wealth or wealthy or wealthier or wealthiest. It's a similar concept. And so a query that contains wealth or wealthy or wealthier or wealthiest should match this piece of text. And a stemmer is going to bring all of these terms to their root form. You can see that there are some, you can see that there are some sort of oddities about what a stemmer does. For instance, it removes the entire suffix from industrialist. It removes the Y from Tony. It removes the ing from forcing. But this again, it's opening up the set of matches that you can get against this. So this is what actually is going to go into the index, and that's important to remember as well. When we roll all that up together, we can see here a text query that I'm getting from my movies index. I'm searching against it, and I'm searching for all capitals steel. What comes back then, oh, and we're looking in the plot field, by the way. What comes back to me matches steel for both lowercase stealing, steal. This is kind of the intent and what we should expect to see coming back for the query steal. So our final topic to consider is relevance. And relevance is where the rubber really meets the road in that big problem that I described of I have a big pile of information, I need to pull the right stuff. Well, what is the right stuff? And there's no out of context answer. There's no objectively correct response for any query because every query is issued in the context of some goal. Usually when we're talking about a search workload, it's a user goal, either for information or to support some other goal in their life, right? So if I'm running an e-commerce engine, or actually let's stick with our movies example. If I'm running a streaming service, my user has a goal to be entertained, right? And they're going to send a query that will pull some set of documents, which are movies. How we rank them really relates to that particular user and that user's entertainment goals, right? There isn't a way to objectively determine whether a particular movie meets that user's goal. It's subjective because it's that user who's going to say it. So having said that, we have some statistics that we frequently use to evaluate search results, but most or all of them require some kind of prior intervention where a particular person is going to look at these and decide, for this query, was this actually the right result? So the common statistics that we apply, precision and recall, you'll hear those quite a bit. So the precision is the fraction of the search results that were returned that were relevant for that query. And the recall in this case is the fraction of all of the relevant results for that query that you returned. So when talking about search engines, you'll hear people talk about precision and recall. The important thing to listen for is the results that are relevant is, again, relative to a particular query and a particular user goal. We also have a couple of statistics that we look at in terms of the ranking of the results themselves, right? So they're all related to sort of where is the correct result in the set of results that were returned. Mean reciprocal rank just looks at the average, the inverse actually, of the first correct result. So if the first correct result was 4, then you get a quarter, 1/4 score. If it's first, you get a 1, that's the best you can do. The cumulative gain and discounted cumulative gain sort of augment that a little bit by looking at the number of relevance results, discounting them for precision in basically the same way as mean reciprocal rank does. When we also evaluate, there are signals that we can look at to decide whether this particular set of results was actually relevant, right? So from a client side, I know that when I'm running my streaming service and I set a set of search results back, and my customer actually clicks on one of those results, that was actually something was relevant about that. And I can track that on the client side, as we'll see, and I can feed that back in to further adjust in the future. A purchase is actually even a stronger signal. If somebody actually laid their credit card down to buy something, then I know for sure that was relevant for that particular thing, for that particular query. And depending on domain, there are many different signals that you can pull out of the client-side interaction with the search results themselves. Next slide. The relevance information can be either static or dynamic, right? So, and this corresponds to the 2 different timeframes where OpenSearch is actually interacting with the data itself. So at index time, the application and you will actually know certain things about your documents and your data set. So you can enhance documents with entities. So you can do entity extraction to provide additional targets for matching. You can do keyword extraction. Those can make documents more retrievable or retrievable based on a higher level concept match. You also frequently can add information like user ratings, likes, shares, other social media. All of that sort of static or compile time, index time, if you will, information can improve your ranking because you can build a rank function to bring that into play. You want to generally augment with clicks and purchases. So again, those signals that you have, you augment your documents, you put those signals on there, whether it's some machine learned addition to those signals or whether it's some aggregation of those signals. In some way, you want to bring those signals back to your data set. Then you have sort of some criteria that are just really real time. Things like whether something is in stock or not. Somebody is on your e-commerce site and they want to buy something. If it's not in stock, that makes it less relevant for that moment. All of that can be done at index time. This is all static information that you know at the time when you send that document in. You also have query time information that you can use to augment the query itself and do a better match and a better ranking based on a particular customer, particular user who is querying that data. So frequently we look at personalization. We look at preferences in terms of brands or sizes or colors. Stuff that I know about this particular user can be added to the query itself, and the query you can rewrite the query so that they retrieve a more accurate or a better set of results that fits that particular querier. On the back end, and when we're dealing with text matches, there's a core scoring function in Elasticsearch. This is called generally TF-IDF. There's a specific flavor called Okapi BM25 that is the actual implementation of TF-IDF, if you will. The idea here, and why we talked a lot about the decomposition of text, is that when you look at your corpus as a whole, you have a certain frequencies that the different terms are going to appear. Some terms are going to be very common. We talked about stop words like a, and, to, the. Those are going to be very common, right? But there are going to be some terms that are very specific. And so when a term matches from a query to a document, you want to take into account how valuable, how discriminative that term is across the corpus of documents. So we look at something called inverse document frequency. It's 1 over the occurrences in the corpus as a stand-in for the value of the term itself. And then we want to look at how often does that term occur in this particular document that I'm scoring. The idea here is that rare terms or very discriminative terms that are in the query and in this document and that occur frequently in this document are more valuable. They'll give you a better match. Again, but what happens is this is a statistical measure. And so you don't get a lot of discrimination or fine-grained differentiation where you have similar scoring terms that occur in similar amounts. In other words, if your document set looks the same statistically, TF-IDF is not actually going to give you much discrimination at a fine grain, right? So that's where we start to bring in these static items like freshness or quality or ratings, and where we start to use the user-based information to further discriminate beyond what the statistics for TF-IDF can actually provide us. And we build rank functions to include not only the document information, the queries include the user information, and between that, that's how we get to a good ranking for a set of results.
Okay, well, that was great, John. I really appreciate you explaining the concepts, and they really are the kind of core understanding to get you forward in an open search, and they're at the center of if you're using it or wanting to, contribute to it. These are all things you're going to have to know. So let's move into the next session, part of the session where we're going to talk about how you can contribute and how you can get involved. So GitHub is, for almost any open source project, and OpenSearch is included, the kind of core of the interactions that will occur. This is where the source code lives. Now, with the OpenSearch project, it really starts with the GitHub organization. Now, I did mention earlier in the talk about how it was organized, and that you had the two core pieces, OpenSearch and OpenSearch dashboards, and then from the lineage of Open Distro for Elasticsearch, you had a number of plugins that add functionality. So that has carried forward into how the structure of the GitHub organization works. So OpenSearch project is our GitHub organization, and we have two pinned repos in there, and that's OpenSearch and OpenSearch dashboards. Now, you'll also notice if you were to go and just browse through that, there's a whole lot of other repos in it. Most of these will fall into this similar pattern. The functionality will be split out into two distinct plugins. One plugin for OpenSearch and one plugin for OpenSearch dashboards. So this follows the same type of patterns that you would have for other parts of OpenSearch and OpenSearch dashboards. So on the OpenSearch side, you have the things that are doing the indexing, that are storing the data, and providing the core parts of that functionality. So if anything happens there, it's going to live on one repo. In this case, it is not usually marked. So in this case, you have anomaly detection, which is one of the plugins. So if it doesn't have dash dashboard in it, or dash dashboards, excuse me, it's going to be the OpenSearch related one. Now, on the other side of that, we have the dashboards plugin, and that's more of the UI and the front end part of that. Now, navigating this organization can be a little bit challenging, so it may not be the first place you want to start because just finding out where to contribute can be kind of hard. So let's talk a little bit about how the other kind of non-mechanical parts happen and the project communication occurs. So opensearch.org is our website. From opensearch.org, you can find a link to our forums and as well to our blog. And then you also have lists of news and events as well. So the forums are actually where a lot of the actual work happens as far as getting to know about the project and where you can contribute. The way we've divided this up in this particular project is if it's a conversation point, it goes on the forums. If it's something that is more mechanical, so an issue or a PR, that goes on to GitHub. We kind of made that division for a couple of reasons. The forums provide a little bit nicer of a way to both interact and build up your kind of OpenSearch specific set of information, but they're organized in similar ways. So for example, we would have, most plugins do have a category in the forums where you can talk about, for example, just anomaly detection or the security plugin. The blog is an open source blog, and the reason we have it, we call it an open source blog, is it's open to contribution. So if you want to write a blog post, let us know, and we'll walk you through the process. But really, it's written in Markdown, and you can contribute on GitHub. It is one of the many repos that you would find in our organization. Now, events, we are in a weird spot in the world right now for events, granted. There's not going to be anything but really online events for quite some time, we think. So that's going to be all the online events. So for example, we would post this conference itself on an events page. And indeed, we'll do a specific type, which is one of our regular events, which is our community meetings. We have community meetings bi-weekly. Those community meetings are held over Zoom, and they're a little bit different than maybe a traditional community meeting in that we have a hybrid format. The first part of the format is to, disseminate news and information, kind of. So in that regard, we have presentations about stuff that's going on in the software and maybe RFCs, requests for comments. That would allow people to give feedback and structure that feedback in a way that wouldn't be really easily facilitated in a non-asynchronous manner. So we do encourage you to join them. The other part of that is the bidirectional nature of this. It is an open Zoom meeting, and some of the best community meetings we've had is when community members have asked one another to solve each other's problems. And honestly, I find that to be one of the more unique parts of this regular community meeting that we have, is people are willing to speak up and help one another through something tough, because our team that is here, or the other people who are contributing to it, they may not have experienced what exactly a user's experienced, but multiple users can connect with one another and say, well, actually what you might want to do is try something different or another tactic. So it's a really great place for that. So that's all the time we have for today. I want to thank you. Please do keep in contact. You can find myself on the forums. I'm Searchy McSearchface. You can see my love of search right there. Only slightly regret using that name. Or you can find me in all these social media profiles as well. Okay, thanks for your time. It's been great. Have a great conference.